This video is sponsored by PCBWay. Welcome everyone. This is another video on the TCD1304 spectrometer series. I made some updates regarding the software I used to obtain the spectrum, and I also noticed a relatively big interest in this device among my viewers since I published a short video on this device. So in this video I will follow up the most recent updates and I will show you some interesting measurements. I'm still using the same B&W Tech BTC100 spectrometer. I bought the housing with all the optics in it, but the lid and the CCD was missing. So a few years ago I designed a board that fits the back of the enclosure, and then the board, as you might guess, contains the TCD1304 linear CCD. Recently I revised this exact PCB and slightly improved the circuit layout and also shrunk the board. Otherwise it stayed the same function-wise. Then this same CCD carrier was turned into a board that can be directly mounted on the top of an STM32F401 CCU6 microcontroller. This is a very compact solution that allows a convenient driving of the TCD1304 linear CCD. You can see that the two boards barely differ. However, the one for the microcontroller is slightly wider because I needed a little extra space for the pins. If you are interested in these breakout boards, visit my project page on PCBWay's website and use their services to get one for yourself. Or if you have other projects that require PCB manufacturing, 3D printing, CNC machining or other similar manufacturing processes, visit their website and use their services. Plus, if you feel extra creative, check out their ongoing 11th badge design contest and join it by submitting your design. The spectrometer has an SMA connector that allows to couple the light source in it in a professional manner. My fiber optic cable has an SMA connector on one side and an FC connector on the other side. As a reminder, let me show you the insides of the spectrometer. As I mentioned earlier, the device came without a lid, so I measured all the dimensions and designed and printed a new one for it. It fits well and it seals the stray light perfectly. The other thing that was missing is obviously the CCD. I actually improved the original design of this spectrometer because the original one had a Sony ILX511 CCD with only 2048 pixels instead of the 3648 pixels. If you look at the other parts, we have the grating mirror with 1800 lines per millimeter. This optical element splits up the light into its components. Then we have the focusing mirror that focuses the light coming from the grating mirror onto the surface of the CCD. Then we have a collimating mirror that reflects the light coming from the slit onto the grating mirror. And of course we have the entrance slit that has a tiny 50 micrometer hole in it. As I mentioned, the new CCD board is not made for this specific spectrometer. As you can see, it is slightly smaller than the old design that sits in the spectrometer, but it still can be used for other designs. So after this brief refresher, let me tell you what I'm going to show you in this video. One of the main attractions in this video will be this high pressure sodium lamp. It has a very interesting spectrum and I want to show it to you. Then this fluorescent light will be the most important device in this video because I use the spectrum of this lamp to calibrate my spectrometer. It has a messed up spectrum, but it is perfect for calibration. I also have this huge grow light from IKEA. If you look closely, you can see that the LEDs at the outer perimeter and in the center are different from those in the inner ring. So in this video we will see how their spectra differ. This bulb is an ordinary LED light source from another Swedish shop, and I want to see how its spectrum looks like. And finally, I have this LED filament lamp. It is bright, so let's see its spectrum as well. As I showed in my previous episode on the spectrometer series, I made a little enclosure for the lamps. It is a simple metal box with an E27 socket in its lid and with two connectors for the fiber optics. One is at the end for the lights that emit light in a straight trajectory, and one is at the side for the lights that emit light radially. And for my sodium lamps, I have one more, I just didn't show the other one. I have a separate igniter circuit as well. It has been quite an investment to hunt down all these components for this project, but I hope it is worth it. Finally, before looking at the different spectra, let me show you the spectrometer in action. I will use this fluorescent lamp as a light source for this demonstration. You can see that a tiny amount of light is coming out from the fiber optic. This light will bounce across the spectrometer's optical elements and finally fall on the CCD. I put a piece of paper in front of the CCD so we can see the spectrum that would reach the CCD without the paper in front of it. We can see a bright green and bright orange spot on the paper and also some faint light in between. Memorize this pattern for future reference. So now you saw how my setup works. So let's go to the computer and let's see all those spectra and software stuff. So right now we are looking at the software that I made to capture and visualize the data from the TCD1304 CCD. This software has multiple functions. We have 3 acquisition modes: single exposure, spectroscope, and scanner mode. The single exposure mode is just capturing the line coming from the CCD. The spectroscope is obviously the spectroscope, which we will use in this video. And finally, the scanner mode can be familiar to you if you have been following me for long enough and if you have been following my projects with this CCD, because this scanner mode is used to basically scan the image plane of an objective lens. So basically, if we build a scanner camera, then we can use the scanner mode. But now we are going to use the spectroscope mode. So I'm just connecting to my microcontroller and I just select whatever high enough exposure time, because we have quite bright light. And then I just start receiving data in this single exposure mode. And now you can see that we don't see anything because I haven't plugged in the light source. But this is perfect because then I can do baseline subtraction. So what we do here is that you can see that we have a signal which is about, let's say, 500 units high, and that is just the basic signal which is coming out from the amplifier. And this is due to the fact that I haven't adjusted the resistors correctly. So the 0 signal output of the CCD already has some elevated voltage, let's say, but I can get rid of this by applying a software manipulation. So when I click this button will fix everything, because it will store each pixel's value in an array. And then when I click the checkbox, then it will subtract those stored values from each subsequent captures. So now I just press this, so I just get a message. I just print these things for myself. And then if I click this, the line should disappear. And it does that. You can see some floating very close to the axis here, the x-axis. And that is exactly the line with the subtraction. So without and with. So now I stop the acquisition and I go to spectroscope mode, and this is one of my updates. So previously I was using a linear fitting. It's basically just 4 numbers, and I fitted everything along a straight line. And I have already done the homework here. So I have already calibrated the system with the light, with the fluorescent light. So you can see 4 different points in this chart. This is also an update, so I can see how the data is fitted. And I fitted a 3rd order polynomial on these 4 points. And this is how it looks like. So you can see that it's really a curved line, obviously. But really, if you would put a line over this, then there would be a big deviation between the given wavelengths at higher pixel numbers or bin numbers, and also there will be some slight deviation here towards the lower wavelengths. So it's good to have this fitting, and you will see that this works very well. So I just apply this, and then the software also automatically calculates the minimum and maximum wavelengths that are possible with the given number of pixels, and basically what will be the available wavelengths range. So I close this, and then I just start capturing again, and we don't see anything. I just show you again that now we have the color-coded chart, but we don't have light. So I just turn on the light source, and we have a light source. And you can see that everything shows up very nicely. And I can subtract the baseline, and it looks even more amazing, I would say. So I just save this. And we have some main peaks here, which are very nicely showing up. So here we have one peak, and actually this is a bit flat because the sensor is already saturating. I can prove it to you by stopping and increasing the speed. So you can see that now it's a bit less flat, but I can further improve this. Now we have a pointy peak here, or more pointy, and this is at 546 nanometers, and the peak next to it is 542. I will do this during the editing, but if we compare this with the chart, which is available actually on Wikipedia, then you can see that we can use these peaks very well for calibrating the spectrum. And as I said, I selected 4 peaks from this spectrum, like nicely separated, as you can see. So one is at 436, so one of the peaks down here. Another is 542, that is this peak. And then 587, which is one of these peaks. I think it's this one. And then 611, which is this high peak. And then based on that calibration, then I can identify further peaks. And here I have to tell you some very cool fact. The person who captured and shared that peaks or spectrum on Wikipedia regarding the spectrum of the fluorescent tube, which you can also see now real-time captured, found my video. And then we just had a nice discussion under the previous videos comment section. So yeah, if you're interested in some details, just go back to the other video. But it was so cool that yeah, he found a reference to his own work by looking at my video. And then for me, it was also cool that he discovered my video. So yeah, that's that. So this graph is not only showing us a nice spectrum of a fluorescent tube, but this is now already also calibrated. So now if I select another light source, we will be able to see its spectrum with reliable wavelength information. So let's check another light source. So this is another light source. You can see it has a relatively flat spectrum. You can see that the signal is quite low, so I can increase the integration time. And you can see that this has a relatively smooth curve, or yeah, it's a bit bumpy, but what I mean is that it's relatively well distributed. And you can see that the main component of the spectrum is in the warmer color region. So I don't know if you can guess what light source this is, but I can tell you. This is the LED filament light source. So this tries to mimic tungsten filament light sources spectrum. And yeah, it's like close enough, I would say. If I increase the integration time further, then I actually saturate the sensor. So let's go back a tiny bit. So this is how it looks like. I captured this chart as well. I will upload this to my website. So then let's jump to the next light source just to see something interesting. So this light source will have probably a rather similar spectrum, but let's see. Well, quite disappointing because it's almost identical. The only difference is that it's a bit less bright because this is the other LED light source which has an opaque cover, and maybe that's the reason why it is a bit let's say less bright or more dim, because yeah, it's not a transparent glass that surrounds the LED light source, but it's a white opaque plastic cover. So that's what you see here. So that's not too interesting, but still I saved this spectrum just as a reference. And then I stop this and prepare the next light source. So this is now the maximum integration time that I can currently reach with my software and the firmware on the microcontroller. And you can just see these tiny bumps, and I can explain you why. This is a pure tungsten filament light source. so this incandescent light. And the problem, or not problem, but for this video's sake, it's the problem. So the problem is that here in Sweden, you cannot really get the, let's say, 100 watt tungsten filament light bulbs anymore, because everything is going towards power saving and environmental friendly things. And of course, they waste a lot of power compared to the other type of light sources. So I cannot source them. And the only light I could find is an 11 watt of power instead of 100 watts. So therefore I get a very tiny intensity. The fun fact is that the previous light source, which was rather bright, that was just 9.6 watt, but it's an LED light source. So you can see that even with a much lower integration time, I think at least 5 times, I don't remember the exact, but I will check it when I edit the video. But at least 5 times less integration time, I got a much higher intensity. So then you can imagine how much power is wasted with the tungsten filament. So now this light source, as you can see, it's rather wide, and you can see the integration time is very short, so the brightness of this light is quite high. And this is the grow light. And this light, which is now captured on this spectrum, is coming from the outer circle, so the more white light. And that you can also see on the spectrum. So we have a lot of blue components, and then the rest of the components, except this region between 475 and 495 nanometers, is quite equally distributed. So then you can see that we have a lot of green and orange and red components, however not very high wavelengths red lights. But as I showed you when I showed you the light source, there are 2 rings, 2 different light sources in this. So let's look at the inner ring, which consists of 5 LEDs. So I try to adjust the light, and there is the missing red light. So this is the red light, which is coming from the inner ring, and this is actually the red which is missing on the previous spectrum. As if I can go back a bit, that's this guy, I capture it. And then going back to the red, I even oversaturated the sensor a bit, something like this. So this is coming from the red LED. So this is it. And now for the final light source, I have the sodium lamp, and that will be very exciting. So let me prepare it. So this light is somewhat special, not only because of its spectrum, how its spectrum looks like, but it also needs time to build up its brightness and stuff. So it takes 2 minutes, and we will follow it in real time, how the spectrum forms in front of us. And when I turn it on, then we will see some peaks, and they will develop and things like that. So we will see how it goes, and hopefully I will manage this for the first try, because otherwise I will have to wait until the lamp cools down and start it over. So I select some relatively high integration time, so I can see the peaks when they start to form. And then gradually I will stop the measurement and switch to a lower integration time or faster integration time. So lower I mean by shorter time, because the light source will become brighter and brighter, so I will have to compensate for that. So I just start this, and of course now we cannot see anything because I haven't turned on the light, so let me do that. And the light is started to shine. We can see a little peak here. Probably we need a bit higher integration time. You can start to see this guy growing here and this, and my sensor starts to saturate. So I just jump down here. And again, the sensor is getting saturated on this at this wavelength. We can see this peak climbing and catching up with this, which is saturated. So I again decrease the integration time, although we will lose these peaks here. But this is the most exciting part here, that this is what I wanted to show you basically in real time, that this one peak is now splitting up as the lamp is becoming hotter and hotter. I can also feel on the metal enclosure that the lamp is getting hot, and actually on its packaging it's written that the lamp itself can become more than 300 degrees Celsius, so it can be very hot. You can fry eggs on it if it would not blow up. But yeah, for fun I check what happens if I increase the integration time to a higher value, because I'm curious about the peaks here. Yeah, they show up, but then this is destroyed. So I actually moved down just a tiny bit, like this, so we can see these peaks much better. Save a picture of them. And now I think the lamp reached its operating temperature, because now it's basically impossible to touch the light source's cover, that metal box that I showed you earlier. So I stop the spectrum here and turn off the light. And then we can see what we have here. It's a very nice spectrum, and I think it was very cool to see this peak to split up in real time in front of us. This was just one single peak, and as the temperature of the lamp increased, then this peak became two peaks. And then also these guys here started to show up at higher intensity. So everything looked very nice. And then finally, I just want to show you something, because previously I also showed an example that we can calibrate our spectrometer using lasers, because the lasers' special property is that they have a fixed wavelength. It's just a single wavelength that they emit, and that's how their color is determined. That yeah, obviously the wavelength that they emit is the color. Therefore, I will just start this stuff again. I mean the spectrometer, and I will shine two different LEDs on them. So I change the integration time to the lowest possible, because we are talking about lasers. And then I shine the first laser on the slit, and there we go. I just stop this so I can catch the peak better. There. And magnify, and let's say I put it here. So this said 653.5. If I look at my laser pointer, it says 650 plus minus 10 nanometers. So this is spot on for me. This is very good. And again, let me emphasize that I calibrated this spectrometer with my fluorescent light. So even though I calibrated with the fluorescent light, I get back the lasers and wavelengths perfectly. That's what I tried to say. And then I have another laser. You will see the color of it very soon. Oi, I kind of destroying now the CCD. Try to be gentle. There. Can you guess the color? Well, you don't need to guess. So this has 532 as a wavelength. If I look at my laser pointer, it says 532 plus minus 10. So again, this is spot on. And again, this is the result of the calibration of 4 points using a fluorescent tube. So once again, thank you who uploaded that fantastic chart to Wikipedia, because I used that to check which peak has which wavelengths on my spectrum, and that allowed me to calibrate it basically perfectly for my home use. I don't think that many people can say that they built their own spectrometer at home, especially with this kind of things, that they develop the CCD driver board and the firmware and this software themselves. So yeah, a little flexing, but whatever. So yeah, that's that. And I will try to find some cool applications of this spectrometer. Obviously there are many, but I will have to find something which is affordable enough so I can buy gadgets for it. We will see what I can come up with. But I'm pretty sure that this is not the last video on this spectrometer. So this is it. If you have any suggestions regarding this software, or what I should do with the spectrometer, what I should demonstrate or measure or something like that, please let me know in the comment section. And if you think that my work is useful and entertaining, or whatever positive thing that you can find about my work, please consider becoming the member of my channel. You can support me, and your continuous support can help me to buy more gadgets and invest into these kind of things, so I can share more hopefully useful information with you. And also don't forget to visit my website. I uploaded the captured spectra there, and I also wrote a little article and so on, so that could be interesting. And also I put the links for my PCBWay project page there for all the 3 different CCD circuit boards. So if you want to buy any of those or build yourself, you can follow those links and go to PCBWay's website and check everything out and purchase what you would like to have. So I hope this video was useful to you. I hope you learned something, and see you in the next video.